Welcome to this session of Python and Research. My name is Jamaica Marshall, and I am the manager for Shadow the Scientist and Python and Research. I know we got started a little late, so thank you for waiting. We're going to go ahead and jump right in with an introduction by our mentors of who they are, and then we'll get started with an quick intro to Python and Research by Raja Guhathakurtha, which I think most of you know as the founder of Shadow the Scientist, the Science Internship Program, and Python and Research. Let's start with Madeline, who is going to be leading one of the leads for Notebook One. Madeline, welcome.
Hi, everyone. My name is Madeline. I'm a fifth-year PhD student at Santa Cruz, where I study exoplanets, which are planets around other stars in our galaxy. I'm excited to be here with you all today.
We're excited to have you, Madeline. Thank you. Next, Aparajito, welcome.
Hi everyone. I'm Aparajito. I'm from India and I completed my master's in physics. I specialized in astroparticle physics and I've been working with Raja for a few years now. I work with ISM spectra of nearby galaxies. So this sparse gas and dust between the stars. We take that and we find the spectra and we do stuff with it. You will learn what a spectra is and how and some things about this process in some of these exercises. Yeah, and I'll be taking over some of the notebooks today.
Excellent. Thank you so much, Aparajito. Geronimo, welcome.
Thank you, Jamaica. Yes, I am Jerónimo. I am originally from Colombia, but currently finishing my master's degree in astrophysics in France. And yeah, I am currently working on astronomical instrumentation, so mostly focusing on the development and kind of scratching our heads a little bit on how to make the instruments that capture the light of the stars that we want to study and learn from, and then analyze the data with some of the tools that some of you are going to learn to use today. So pretty exciting to be here. And yeah, today I'm going to be mostly helping out with some of the questions in the chat, and tomorrow I will handle some of the notebooks that we're going to be working with. But yeah, very excited to be here.
Wonderful. And Raja, and before I get to Raja, let me just say, because I have questions coming to me. Yes, I know some of you are having issues getting into Slack channel. I'm so sorry about that. You will be able to just add your questions and comments here in the Zoom chat. Just make sure the question is going to everyone. When you post it in the Zoom chat, and I will make sure that Madeline, Geronimo, Raja, and Parajito see those questions so that they can be answered, and they will be in the Zoom in the transcript, which I'm happy to share as well too. And so if you have questions, you can directly message me. When you go to the drop-down menu, you'll see Shadow. That's me. Just go ahead and send me that message, or you can post it in the chat to everyone. All right, and so last but not least, Raja Guhathakurtha, who is, of course, the founder of Science Internship Program, Shadow the Scientist, and Python and Research. Raja, for those who don't know you, please give us a quick introduction and tell us a bit about this wonderful tutorial. Oh, you're muted, Raja.
Sorry about that. Thanks very much, Jamaica, for setting this up. I know a lot of hard work has gone into organizing this, and many thanks to Maddie, Kero, and Aparajito for being here to really run this tutorial. I'll do an introduction in two parts. I'll say a little bit about myself, then I'll say something about the tutorial you're about to experience. I'm a professor of astronomy and astrophysics at the University of California, Santa Cruz, which is the institution out of which Python and Research and the other programs that Jamaica mentioned, Shadow the Scientist, Science Internship Program, these all run out of the UC Santa Cruz campus. We're one of 10 campuses in the University of California system. And so I've been doing research at UCSC for 31 years. I've been doing astrophysics research for another 9 years before that, so a total of 40 years. And You'll see in a minute when I talk about the tutorial that this is very closely connected to research. The R in Python and research, the PYAR, research is very much a part of this tutorial. It's not just about Python coding. What is, a couple of other things I'd like to say about myself is not only have I been doing research for 40 years, I've been working with students for a very long time, and pedagogy and education has been a big part of my career for nearly 5 decades. So there are some elements of pedagogy, of course, in a Python tutorial, and but the pedagogical element of the tutorial you're about to experience is not something I should take credit for. It's really the work of one of my PhD students and further developed by 2 other PhD students. I'm going to name their names. Claire Dorman, Emily Cunningham, and Amanda Quirk have contributed greatly to the tutorial you're about to see. In fact, the tutorial is based on Claire Dorman's PhD thesis. So there was a particular paper from her PhD thesis that was published 10 years ago in 2015. And it's not often you see this in a Python tutorial, but this particular coding tutorial is joined at the hip. It's really closely connected to that research article that Claire wrote in 2015. This was the last of her thesis papers, and her pedagogical brilliance is evident in this tutorial. What she did was she took the lines of code that she used to generate plots for the paper, this third paper from her thesis, the last paper from her thesis. She took those lines of code and commented them extensively. So there's not just a line of Python code, but there's a line of English that explains what that line of Python code does. So that's the first step, is commenting your code very precisely. She then removed strategic lines of Python code from this block of code, so that when you remove lines of code, it stops working. So this tutorial will consist of writing lines of code back in. This will be true of 4 of the notebooks you'll experience today. Maddie will talk about notebooks. Maddie, Aparajita, and Hero will talk about what notebooks are, the structure of how code is packaged. But there are 6 notebooks in total. 3 we covered today, 3 tomorrow. And the first 2 of today's notebooks are pure Python. They're not about astronomy research, but the third one is about research. And all 3 Python notebooks tomorrow are about this research article. But I've thought long and hard about why Python and research is different from other coding tutorials. And I'm actually going to put these things in the chat. There are 5 ways in which this Python tutorial is different from other coding tutorials. And I know I've just put this in the chat and it's going to scroll away from you, but you learn Python coding, but you learn it in the context of its application to astronomy research. Very specific research project, of course, but through this tutorial, you also learn the general structure of a scientific research article. In this case, an astronomy research article, but you learn the general structure. And Maddie, I was just seeing your screen where you annotate the article and you talk about the different elements of a paper. That's a learning point that you often don't get from coding tutorials. The third thing you'll learn in this tutorial is you'll get a little bit of astrophysics background, and that may be more relevant to some of the participants today than others. Those of you who are doing astro research will benefit from that aspect of the tutorial, the astrophysics background. You'll learn some technical skills that are relevant that should have read relevant for astronomy and astrophysics research. So you learn some technical skills, statistical tools that are important. Things like the magnitude system, the color system, Doppler shift. So there's some technical aspects to this. And the final piece that I often don't see in coding tutorials is not only is this one connected to a research article, the 4 of us, mentors here, Hero, Maddie, Aparajita, and I, are actually doing research that's similar to this. We're using similar techniques. We're measuring Doppler shifts, we're measuring spectra, measuring color magnitude diagrams. So you're hearing from people who are doing research. They're the ones, we are the ones running this tutorial. I'll stop here. if there's a question, but maybe we should move right on to Maddie, but I don't see any questions at this point.
That's right. Maddie, please get us started with notebook one.
And again,
And
I'll
for
hop
those
off
of
and
you
hop back
putting,
in.
okay,
Sorry.
thanks, Raja. So again, please post your questions here in the chat. I'm going to put several links to the Slack channel in the chat, in the Zoom chat. If you aren't able to join, no worries. We apologize for any issues you're having there. But of course, you can put your questions right here in the chat, and I will make sure that Aparajito, Geronimo, Raja, and Madeline, if she's available, she'll be leading the first part of the notebook, but I'll make sure that they get them. And so if you have a question, please put that in the chat. Don't raise your hand, just put it directly in the chat, and those will come directly to me. All right, Madeline, please get us started with notebook one.
Thanks. And if anyone has a question that needs immediate answering, I'm going to be relying on my co-mentors to help me notice that because I can't see your chats pop up at the top. So just be patient if you want me to answer it in person. All right, so everyone has one Python intro pulled up. If you don't, take the time to do that now. Okay, so at the top here are a bunch of incredible resources. Pretty much everything you would want the answer to in Python, you're going to be able to find on python.org or the tutorial. But once you've gotten a basic grasp on Python, one of the most helpful tools you're ever going to use is called Stack Overflow. And this is essentially a forum, kind of like Reddit, where everyone posts their questions and everyone is able to provide community answers. And this is an incredible resource. Now, we're in an age where you all, I'm sure, are really, really competent AI users. And as you may have heard in your classes, there's a lot of times not to use AI. For example, when you're writing, it'll hallucinate things that are fake. But sometimes when you're code editing and when Stack Overflow has not been able to provide an answer to you that is clear and able for you to understand, consider using a tool like ChatGPT. However, I will say, if you do not develop the basic Python tools, you're not going to know what you're copying and pasting, and you won't know how to edit it when and if ChatGPT hallucinates, which it often does. I've had it make up things on me many times before. So that's a word of caution about using programming-based AIs. So what we're going to do today is we're going to learn those basic skills so that hopefully you'll be more literate and more able to use the tools at your disposal. Okay, so this is what's called a Jupyter notebook. You can run Python in just single programming windows, but the nice thing about a Jupyter notebook is it allows us to run code in little bits and pieces at a time, and also do things like annotate it called markdown cells along the way. That's things like this hello world or these descriptions here. So let's run our first and most classic prompt. Hello World is famous in the programming world for many reasons, not least because the ability to print out what we're doing so that we can get information about how well our code is running or where it's breaking is really important. So let's do our first print statement. Now notice the way that you write print in Python is by writing the word print, all lowercase, and in parentheses, so no spaces, just parentheses. And then whatever I want printed in here, if I want it to be what's called a string, which is some like words we would say, versus a number or a float, I'm going to put it in quotations. Double or single quotations doesn't matter. So we execute that cell, we get hello world. Congratulations, you've run potentially your first, potentially your 100th computer command, print hello world. All right. It isn't just a big deal because we're outputting text. Look at how much simpler it is to do this in Python than it is in Java. This is how we would have to do it in Java. And now Java and C++ are incredibly powerful languages. They run very, very fast. They are better backends for things like how your web browser runs and stuff like that. But when we're doing scientific computing, we don't necessarily need to be super coders. We mostly just want to be able to interface with our code in a way that is easy for us to understand so we can quickly do science. So let's explore some of the things we can do with science. By the way, I want to mention these caution signs and common pitfalls. So take a second to read these. So if we were to execute this instead as print, and I'm going to edit this just directly here, and then I type print again. So I'm just following the instructions of the pitfalls. And remember, I have to close it off because it's a string with quotation marks. Oh, it doesn't like that. We have to put it on a separate line. And we see that it prints out on 2 separate lines. So that's what that word of warning was about. Now we're going to scroll down to doing math with Python. So we learned how to interact with a string, and we'll learn some more about that. But the nice thing is that instead of having to go to, your phone calculator or maybe your TI-84 or even Google, you can actually use Python just to do basic sums. 2 plus 2, okay, 4, we expect that. 4 minus 2, that's 2. 4 times 2, that's 8. The slash is divided in Python, so 4 divided by 2 is 2. Now here's where things get special. And it always takes a minute to remember this when you're first learning Python. The temptation is sometimes to use the caret notation, but let's see what actually happens if we use a caret notation. I'm going to do what's called commenting this out. You can do that by typing a hashtag or a pound symbol, or on many computers, if you have a Mac computer, it's command question mark, or on a Windows computer, it is control question mark. So let's test this out. Let's actually try doing the version I said a lot of people mistake. Let's do 4 and then a caret, the power of 2. And the caret is the shift above your 6 key. Oh, wait, that actually should not, I actually don't know what that it does. But it sure is not a power, because we know that 4 to the power of 2 is 4 times 4, 16. It appears that that caret has acted as a plus sign rather than a power. So whenever we want to do power, we want to do 2 stars. And just like, PEMDAS or GEMDAS or whatever you've learned before, order of operations does matter. If I want to raise, for example, 4 times 2 to the power of 2, I have to put everything in parentheses. Otherwise, if I just do to the power of 2, what is this going to do? It's going to raise 2 to the power of 2 and multiply it times 4, and we get a different answer. So really remember your PEMDAS, GEMDAS order of operations. Okay. All right, let's do this a more PEMDAS, GEMDAS, with your parentheses and everything. So what the order of operations here would be, okay, 1 plus 1, those in parentheses, 3, times 3. But first we have to do the power, so 3 to the power of 4. Now what do we think this is going to do? Are we going to take 3 to the power of 4/5? Or are we going to take 3 to the 4th divided by 5? It's going to be 3 to the 4th divided by 5. We would have to put it in parentheses, 4/5, if we wanted it to be raised to the 4/5. So if you're ever wondering, am I using an operation correctly? Go ahead and do an easy arithmetic that you already know the answer to test it out, so that when you're doing a longer, more complicated equation, you won't run into issues like, oh no, I'm supposed to be raising to the 4/5 power, and accidentally I'm raising to the 4th and dividing by 5. All right. So now we're going to get into one of the superpowers of Python and really any code. The idea that you can not just use numbers directly, like this, where it can be hard to keep track of them and maybe you have to type them many times, but can we use what are called variables. So much like in algebra, if you've seen algebra before, variables are a container that hold an arbitrary value, and importantly, they store that value. So once I define a as equal to 1, and I just use one equal sign here, once a is equal to 1, a will always be equal to 1 unless I reassign it. So here's where we're going to use our print statement. Now notice here, I don't have parentheses around print. Let's see what happens if, or sorry, quotation marks around this value in here. Let's see what happens if I put quotation marks. We're going to print these. Oh, I just get the letter A. That's because putting quotation marks turns it into a string. We want to just print out the variable. So we just need to put the letter in there, the variable name. We don't need to put quotation marks around it. And indeed, okay, we know that A, we're printing out value of A. The value of A is 1. That's correct. I'm going to keep scrolling down. So say we want to change up what A is. Well, it's just as simple as this. We reassign it by giving it a new equivalence here. And then even in the same cell, you can reassign it again. So let's see what happens when we execute this cell. We're going to print A after it's been assigned to be 1 plus 2, and we're going to print A after it's been assigned to be 27. Indeed, we see that the value of A changes. So this is actually not in here, but I'm just going to do a quick test of understanding. I'm going to add a cell. What if I type print A? What is A going to be now? It'll be the last value we assigned it to be, 27. Okay. So how can we do math using variables? Well, exactly the same way as you do with normal numbers. We're going to sum them together using just a plus sign. And we get the answer of 3 as if we added 1 and 2 together directly. And notice how we can still do that sum inside of the print statement. And because this is the advantage of notebooks versus an individual Python code in which you execute several of them in order to get something done, is that if we go to a different cell, A and B are still going to be A and B. Notice how A is now 1 because we reassigned it to 1 up here. So every time I call A and B and print them out or use them, they'll be the values they were assigned further up. And specifically, not just further up, but wherever we last executed it. Say, for example, I execute this cell here, the one that says 17, and we know A is going to turn out to be 27, and I go down here and I print A and B, et voila, A is 27. So it's not just, it's in what you executed last. It's not necessarily, the sequence going from top to bottom. Okay. So get creative with your names. Don't name every single thing A and B, because not only is it going to be hard to remember necessarily what A and B are, but you don't want to end up accidentally using a value that you think is something else. And oh my God, I forgot I made A 27 instead of 1 earlier. This is an important note that though we can do math on Python, we can't, write it like you write a math equation. The equal sign is not like equals like it is in math. It's truly just assigning it to a variable name. So we're going to do one of the nice little tricks of Python, and that is this notation here, which is instead of having to write out, because it can be, laborious, especially if you're doing it several times in a row, to write A plus 1, or to write, A plus B every time, or to write, A plus 1, and then A plus 1 again, and then A plus 1 again. So what this operator here is doing is simply adding 1. This is the equivalent to writing just A and then reassigning it equals A plus 1. Now I realize I didn't explain that as clearly as I could have. Let's look at this example right here. This is the way we're breaking it out. This is what this operator does. Imagine we wanted to increase the value of A by 1. How do we do that? Instead of having to write this all out, is we use this operator that is plus equals. That just means we're adding to the existing value inside of the variable of A. And we can do the same thing for multiplication. We're multiplying the existing value of A times 3 and replacing A in the variable with the outcome of that multiplication. So take a second, if you haven't executed it already, to make a prediction on what we're going to see. I predict that this is going to be 1 here, because A is 1. Then we're replacing A with its sum plus 1. So 1 plus 1, 2. And then I predict that we're going to take A, because remember A is 2 now, And we're saying we're multiplying it by 3 and replacing that value as the value of A. So I think it's going to be 6. Okay, we get what we predicted. All right, so we've mentioned strings, and the reason I didn't get into depth in strings. Now, Aparito, where are we supposed to switch? Okay, not for another minute.
Yeah.
So strings are what we've mentioned before about being in quotation marks. Strings are really helpful because you can label things in plots. You can print outputs like the output of A is, and then put that there. So let's experiment a little bit with strings. So let's take our classic string of hello world. Now notice how I'm able to assign a string to a variable just how we assigned a number to a variable by using an equal sign. But I have to use quotation marks. In fact, let's see what happens if we don't. This should break if I run it. Yep, it says, I don't know what a comma and exclamation mark are mathematically or Pythonically, so we're just going to stick it back in there so that it'll print out our hello world. Now, before we execute this cell, I want us to look at what each of these functions does. So if we're saying just print the variable of s, pardon me, print the variable of s. S is hello world, so we should probably get a printout of hello world. This lower, so this is something specific to strings, where if you place a dot after the string, no spaces, just dot, and then lower, it is performing a function called lower on them. And we'll get into what functions are, but right now you can just understand that this is going to take our string and it's going to convert it all to lowercase. And then the same thing for upper, it's going to convert it all to uppercase. And it is very important, because these are functions and we'll learn more about them in the future, that you have these parentheses here. In fact, let's break it again and see what happens. I'm going to execute this. Oh, we didn't get an all lowercase version. We got something like this output. And that's not what we wanted, not what we expected. It's just saying, you're doing a method. I'm like, I know I'm doing a method. I would like to get the outcome of the method. So I have to use these parentheses here. Okay, so I've done lowercase, I've done upper. And then the last function we can perform on this string is replacing part of the string, in this case, the word world, with SIP. And it's a direct replacement. You see it completely takes out the word world and replaces it with SIP. Now, an important thing to notice is we said find us the word world and replace it. We didn't say find us the total capital version of world. That's because what we did here to the string is not permanent. It's just to print it out. We would have to reassign it to another variable or reassign it to s in order for that to stick around. So now we've done hello SIP as well. So believe it or not, you can do math with strings. So remember our s. What is the value of s? S is hello world. Well, actually, it's probably. Nope. Remember what I said. You would have to say s equals s dot replace, etc., in order for that to take the place of what s was before. So we're going to have our original value of s, which is hello world, exclamation mark. And now we're going to add it. We're going to add something to it. We're going to add it's a beautiful day, because it is. And then s times 2. What do we think s times 2 is going to do? I actually don't remember because I don't use this function a lot. My guess is it's going to print it 2 times. Let's see what happens. Look at that. So doing some string math, we added the string to it that it's a beautiful day. Notice this little space here. That's not important. You could fix that, but we would get no space between those, which is not proper. So we want to add a space there. And then s times 2 indeed prints it 2 times consecutively. All right, moving on to lists. So lists are lists like your grocery list, or they're lists of numbers. You can have lists of both numbers, aka floats, or integers, or you can have a list of strings. But let's work with a list of integers first. And I'm going to switch from the word numbers to the word integers or floats. An integer is something with no decimal points after it, and a float is something with a decimal point after it, even if it's 1.0. And that's just how your computer handles these different types of inputs. Okay, so we have a list of integers here. They have square brackets. This is really important. They must have square brackets to be a list. Okay, so what if we want to not just use this list? What if I want to get at a specific element in this list? And I want to get at the very first element. What I'm going to do is I'm going to take my variable, which is, well, let's just print this out first. I'm going to comment these all out so we just see the output of x. Okay, yes. X is a list of integers. 1, 2, 3. Okay, what if we want to get at the first? What if we just want to get this value of the 0 and not have it be part of this list and just know what it is? Well, we're actually going to start with this notation. We're going to use square brackets. It is called indexing. And we want to get the 0th index because strangely, Python doesn't start counting at 1, 2, 3, 4. It starts counting at 0, 1, 2, 3, 4, and so on. So what happens here when we index this? Well, let's find out. Okay, we try to take the very first element, the 0th element. We indexed our list x, and we indeed got it to return 0. Now, it's not just returning 0 because there's 0 in here. It's returning 0 because it's accessing the very first thing in this list. If I change this to a 5 in our list, the 0th element would be 5. So we know that it's doing what it's supposed to. Let's print all these other ones out. And indeed, we see that we've accessed every integer in this list individually. That's really, really useful in coding that you do for science a lot. You'll end up dealing with data sets, and being able to manipulate your data sets is pretty important. So moving on, if you try to do, say, what's going to happen if I try to access the 5th element? Oops, outside of the range. So there's not 5 elements in this list, so I can't access the 5th element. That makes sense. Great movie, 5th Element. Okay, so how do we then know how long our list is? Say we can't look at it. Say we didn't type this out. Say we can't look at it and see that it's 0, 1, 2, 3 long. So we need to know the length then. So here is an example of how we can combine strings to give us helpful information. I could just print this out as print and then len, which is the function that gives us the length of a list or an array. I could just print that out and I'd get the number 4. But maybe I don't know what 4 actually corresponds to. Like, what is 4? 4 is meaningless. So let's include a little bit of extra information. Let's tell ourselves, helpfully, this is the length of our list x. And so we put this because it's a string in quotation marks. Remember, it doesn't matter to be double or single. And then we're just going to put a comma. You have to put the comma. And then this, our variable, which is going to be the output of the length of x. And indeed, the length of x is 4. What happens if we don't put that comma? Gonna get an invalid syntax. So remember to put that comma in there. Okay, you have a length of 4. So you can also count backwards. That can also be helpful in scientific inquiries. Say I don't want to figure out, they say this is 100 numbers long, and I don't want to bother figuring out how long it is, and I just want to get the very last number in the list. Well, I can index backwards. Well, this was the 0th, 1st, 2nd, 4th, 3rd index. What if we said I want to go backwards? This is the -1th, -2th, and -3th index, and we can access those the same way. So we're counting backwards. We're going to the -1st, the -2nd, the -3rd, and you get 3, 2, 1, 0. Okay, now slicing is another important ability. What if we don't just want to get the 1st and the 2nd index? What if we want to get everything up to the 2nd? Now, This is a tricky thing about Python, and I remember struggling to remember this when I did Python. Not only did I struggle to remember that like 0 is where you started, this is a tricky thing about Python that is not the same in every coding language. Python is called non-inclusive. And so what it does when we print out this notation where the colon is telling us that we want the 0th through the second index, it is not going to get us 0, 1, 2. It is going to get us 0 and 1, not 2. So we can think of this as saying 0 up to the second index. So what happens when we execute this? Yep, we don't get 2, we just get 0 and 1. So if we wanted to capture the second one, we do up to 3. So 0 up to 3 gets us 0, 1, 2. Perfect. So, I mean, you can get fancy with this. We know that there's like it's gonna start at 0 in this case. If you don't have a 0 explicitly written out, the computer will just assume that you mean 0 there, and so we'll get the same output in that notation. And the same thing for the opposite way is if you do the colon on the other side, where this is your starting point, you're going to start at index 1, and you're going to go to, well, the end in this case. So let's see it go to the end. Okay, so it didn't include the 0th one because we told it start at 1 and go to the end. And of course, you can use the same notation of like negative integers to get fancy. So let's make a prediction about this one. We are saying start somewhere, and you're going to go up to -2. So what do we think this is going to do? Let's see. Oh, interesting. So it's counting backwards through that's going to go from 0, because 0 is implicit, to the -2nd, which is this value here. Interesting. Okay, let's return to our list. Now we know how to slice it into different chunks. We can actually do things like replace the values in entries in a list. So here's our original list of x integers. We can print that out and see that it's the same. And so now, using the same notation of square brackets directly next to the variable, remember that indexed it? And so when before we said the first index of x, like right here, we got an output of the first index, 0, 1. Here's the first index. We got an output of 1. So what we're doing here is we're saying, I want to take the value that's in the first index in our list, and I'm going to replace it. I don't want it to be 0, 1. I don't want it to be 2 anymore. I want it to be 486.1. So let's see what happens after we assign 486.1 to the first spot in our list. Et voila. Now our X list goes 1, 486, 3, 4. Okay, so lists can hold anything. That's why lists are kind of convenient. We want to make a list, for example, of different types of objects, including an integer and a string set off by quotation marks. And oh, look at this, a list of other lists. So what happens when we execute this? We'll print this list out. If we access the 0th index, we should get 1. If we access the first index, we should get a string. If we access the second index, we should get this whole list. Now, last but not least, when we say, okay, I'm indexing the second index, okay, that's this value. But what if I want to pull out one of the values inside of that list? Well, I can just add another index. And this index is going to access the 0th element of the second element of this list. So here's the second element, and here is the 0th element of that. So let's see if all of our predictions were true. Okay, first we printed out the whole A. Yep. Then we access the 0th index, the second index, the first index, the second index, and now the 0th element of that second index. So there's lots of built-in tools for doing lists in Python. So we're going to do some things to make these lists without having to type out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with commas between them all. That's kind of hard and gets tiring. So if we want to make a list of something, all we have to do is use the list function. We're going to put list and then parentheses around whatever we want to go into that list. Now in this case, we're going to use another function. This function is called range. And what range is doing is it's saying, I would like to build. I don't really use these this way, so I'm going to execute this and we'll figure out what it's doing. Yeah, so it's just like a range. Okay, so this is going to start at the number 1 and stop at the number 10. Remember, Python is non-inclusive, so it's not stopping at 10, it's stopping before 10. So it's starting at 1 and going up to 10. And then this here, this third value, look at this array below. What do you think this third value does? That's our step size. Now the step size, if we changed it to 3, how do we think that would change our list below? Oh, yep, indeed. We step from 1 plus 3, 4, plus 3, 7. And look, plus 3 would take us to 10, and it's non-inclusive, so it's up to 10, so we don't include 10. Okay. What if we instead construct a list, and we don't want to step by 2, and we don't want to start at a specific value, and we just put range 5? What happens when we just put range 5? Well, we get a lot of implicit assumptions by Python. Python assumes that this means we want to start at 0, go up to 5, and step by 1. But you don't have to write that all out. You can just write range 5. And remember, we start at 0. Okay. So what happens when you add 2 lists? Actually, I know I'm asking you all to make predictions. I kind of remember this being an already full notebook, so you probably already have the answer in front of you. But I'm going to make a prediction. When I add these like sort of groups of numbers together in math, I would do sometimes 1 plus 0 and 3 plus 1 and 5 plus 2 and 7 plus 3 and 9 plus 4. Is that what's going to happen when we make a list? Nope. This is why lists are different. Lists don't behave like something we'll learn about in the future called arrays. Lists, when you add them together, are just going to tack one onto the end of the other. So we've taken the X array and taken the Y array and tacked one onto the end of the other. What happens if you multiply it by an integer? Do we think it's going to duplicate it, or do we think it's going to multiply every element in Y by 2? It duplicates it. So when you do math on a list, it's kind of like you're doing it on a string. It's going to behave very similarly. Timesing it is going to duplicate it. Adding it is going to tack one onto the end of the other, also called appending. So let's do some interesting things we can also do with lists. Let's make a new list. We're going to say x plus y. Now we know that x plus y is going to append those 2 lists together. And we're going to call that new mega list z. And then we're going to do something called sort. And sort is a function. So remember, we do a dot sort, and then parentheses must have the closed parentheses. And let's see what happens. Notice how these are kind of all out of order here. Okay, all out of order. And then we do sort. Oh, look. Now they are in ascending order. 0, 1, 2, etc. Last but not least, what if we want to add some specific information? What if we specifically want to append just one value or a couple of values to a list? So now our list X is just the values 3 and 2. And if I do the function append, so dot append, parentheses, and in here is what I want to append to it. This is going to append or stick on the value of 1 to this list. And then if we did it again, do you think it would be 3, 2, 0 or 3, 2, 1, 0? It's going to be 3, 2, 1, 0 because we've just appended this. Oh, you know what, guys? No, it's actually not going to be, because if I wanted to redefine what the list of X is, I would have to use something like this. I'd have to redefine X as what we created with this append function. So let's run it and see if my predictions are true. Oh, nope, apparently that's not how lists work. It's interesting because I run into problems when I do this in for loops, but okay. So my original prediction was correct, and in fact, my correction was wrong. This is the fun thing about the scientific process. You don't get to know until you try it. And so that's the nice thing about code is you immediately get the answer. So we've seen that when we run X and then append something to it, it's the same thing as redefining X as the appended value. And so we just add the value of 1, and then we add the value of 0 to this list. Just like that. All right, tuples or tuples. All right, just me. I'm going to move quickly through these. Tuples, tuples, I've heard it said both ways. I say tuple. It's like a list, but you can't change things inside of it. Instead of using square brackets like we did on a list, a tuple is going to be anything defined with these parentheses only. So here we have a tuple of letters, tuple of strings. And if we print it out, we're going to get the value out. And if we index it, we're going to get the very first value. Remember, 0th first. Okay, that's what we expect. Now let's try to do what's commented out here. Let's do the illegal thing. Remember, we can't change a tuple. It's not like a list. So we want to try to index the 0th value, and we're going to try to reassign it capital A. Nope, not allowed to do that. Type error comes up, and that tells us, nope, can't do that with a tuple. Can do it with a list, can't do it with a tuple. All right. Conditionals and booleans. All you, aparejito.
And while we're waiting for Aparajito to take up the next part of the notebook, I want to say thank you so much to Madeline. Awesome, awesome, awesome. For everyone in the chat, first, I've gotten several questions about the recording. Yes, the recording will be available on the Shadow of the Scientist YouTube channel. I put that in the chat, and the link, I'll put it in there again in case it went by fast and you didn't see it, because there's lots going on in the chat. Also, again, if you didn't download Anaconda and install all of that before the session, no worries. Please just pay attention to what's happening right now. Ask your questions in the Zoom chat if you aren't able to get on Slack. And then afterwards, you can go back, download Anaconda, open the Jupyter notebooks, and run this on your own. Please feel free to do that. Also, again, with the Slack channel, apologies for those who aren't able to join. Just put your questions and comments right here in the Zoom chat. Those are going to come to me, Shadow the Scientist, or if you post them to the co-host, it'll come to them too. But feel free to send those directly to me. I will post them to the main chat. As you see, the Parajito and Geronimo have been responding to your questions and comments right there. So very easy to do. No worries, no stress. I do apologize again about that. And Parajito looks ready to go for the second part of Notebook 1. Parajito, it's all you. You muted.
Can you hear me now?
Yes, perfect.
Perfect.
Thank you.
Sorry. One of my applications crashed. I don't know which one. Sorry. This is taking longer than it should.
No worries. Appreciate you.
Okay, while I begin to share my screen, if anybody has any questions, please feel free to post them directly to the Shadow of the Scientist account. like Jamaica said, as she will redirect your question straight to the main chat, and you can get your answer there.
Yes,
Okay.
absolutely. And you'll see for the mentors, for everyone, any questions that I get when I post them, I also put a red question mark underneath it, so it's easy to see where the questions are. So hopefully that will help.
Right. So Maddie has covered the
Oh, wait a minute. Did Apargito? I think we lost Apargito for just a moment.
Yeah, right. I think also he just disappeared suddenly.
Okay, so he did. All right. I'm sure he'll be back in just a moment. Madeline, could you get us started with conditionals and booleans until Apargito joins us again? Or Geronimo?
Yes, I think I can open the notebook real quick. We were at the Booleans part, right? I'm sorry, I got to
That's right.
entertain the reading and making sure I was like replying correctly to the questions. So if you want, let me get it here.
Thank you. And while we're
Yes.
doing that, I'm going to post another question here um, about what is the use case for tuples, and that will be for all of our mentors to answer.
Okay, are you seeing my screen now? I think so, right? Conditionals and Booleans.
Screen share right now, Geronimo.
Wonderful. Okay, I'm just checking that my connection is all good, right? You can see everything, you can hear me, right?
Yes, I can.
Wonderful. Okay, so checking this part, I made sure to run all the cells of the notebook up to the point where Maddie took us. Here we're starting to study different types of variables. That is a very important thing to understand, that the objects that we work with inside of Python or any programming language is what we call a variable. So we were listing, for example, numbers before and gathering together in small lists, and we could do operations with those lists. I was about to just reply to one of the questions that popped up in the chat that was like, can I append one list to another? Can I add two lists together? And what's the difference between that? So that was very interesting from the experiment that we were just seeing. For example, you can have this group of 3 letters, and if you make another list that also has other 3 letters, and you just use the append instance that we will see in a while, you can put them together and you just make like a bigger list that has both, like it has more elements than the original one. But also you can add 2 lists that if they have the right properties, what you do is that you add the elements of the list as specific variables in each position. So that's a bit specific. So we will see it with examples, and that should be more clear. But before that, we should check the new type of variable that is a bit weird sometimes to understand, and is the Booleans. Booleans are a type of variable that has either one of 2 values, true or false. It's pretty much like the basis of computer science in general, because it's what we associate with zeros and ones, right? Like if a position is set to 0 or false, we would say like something is off. Or then if it's set to 1 or true, we would say it's on. And they can be combined with these 2 binary operators that are and or. So we can use them to test conditions in our lists or in our arrays that we will see further down the line. And that can help us, if we have a list of elements, we can also impose conditions to filter some of those elements if we only want the ones that satisfy a certain condition being true. So that's important. Here we have, for example, if we define 2 variables, so we're assigning the 2 variables here. one as true and the other one as false, we can print them as with the operator in between. So if you just do print A, it should print true. If you just print B, it should print false. But the logical statement A and B, if we translate it to what A and B are, is true and false. That logically has to be false. So that's what we're getting here. So when you hit, I'm going to run again this cell. As I was telling you earlier, you can run any cell any amount of times, do modifications, and run it again, and that's the usefulness of the Python notebooks. So if you do true and false, that is going to be false, because the whole statement, like the AND operator, requires both variables to be true, or like both statements to be true in order for the whole thing to be true. A or B then will be true because one of the two is true. That's the property also of the OR operator. And then if we play with the NOT operator, so again, this is in the logical language, not A is the opposite. So if A was true, then now it's printing false, and not B, since B was false, now it's going to be printing true. So this is just a subtlety that is going to be helpful to keep in mind, and we're going to use it sometimes. We don't have to like know exactly how to do all these operations in our head. That's what the computer is for. The computer is like helping us. If we assign correctly the variables that we're going to be using, then when we do operations with them, the computer is going to handle the things that our brains cannot handle on its own. So we can use also a couple of very useful ones. I use these ones a lot when I'm using like filtering lists of I don't know, if I have the brightness of a star, for example, or like the brightness of many stars, and I want only the brightest ones, or I want to set like a limit of like where the exact amount of brightness is. It's useful to check when a number or like a variable is exactly equal to another one. And for that, we use this double equal sign. In maths, for us, it wouldn't make any difference to write 1 or 2 equals in between two numbers. Like that's like just in mathematical language, it doesn't change that much, or like in algebraic language. But in logical language, saying that, or like in computer science language, if you say that A is equal to true, you're assigning the value of A. So you're defining that there is an object called A, and that its value will be true. But in this case, we're not defining a variable. We're asking the computer, is this number on the left exactly the same thing as this number on the right? Which in this case, we can expect already that it will print false, because 1 is not equal to 2. Then we can also use the not equal symbol, which is just adding an exclamation point in front of the equal. And then we have that 1 is different to 2. So like that's gonna be true. And as we see, like it's already printed here, because as I told you, I ran all the notebook earlier today just to check that things were working. We see that 1 is not equal to 2, and clearly 1 is not equal to 2. That's very logical, but we have to start with the simple, we would say kind of dumb statements, because that's the checks that we do, that the programming that we're doing makes sense for us at the beginning. And then when things get more difficult, then the computer is going to be our aid for understanding more complex problems. We can use the less than, or less or equal than, to do the same. So here 1 is smaller than 2, and 1 is also smaller or equal than 2. Both conditions are true, so that's what we see printed here. Same for greater or equal. We have a similar syntax, so it's written in the same way. So we can use this, and this is very useful to set statements, to set like conditions, sorry, that we can introduce into a thing that we call loops. And that's how we run many things in computer science, in science in general. We want to do tasks that are repeated many times, that are difficult for us, for a human or for a group of humans to do. So we can write it down in a code, and then we can do, okay, if this condition is met, run this task, and then run it as many times as necessary while that condition is met, or for an amount of times that I think the condition is met. So we can start writing statements like with an if statement that says that if a condition is held, is evaluated as true, you can do something. So this is very important. And yeah, Python can get not annoying. There's other languages that are more annoying, but Python will require you that when you write if condition is equal to something, you have to put a colon at the end of that, and then you're gonna see this that we call indentation. This indentation is like a space with respect to the margin to the left that lets you know that whatever you're writing here is under the umbrella of that if statement. In this case, we're gonna see that that applies to a lot of things, to defining functions, to writing loops. We're gonna be able to notice that we're in the right spot and we're writing the statements that we want to write by checking that the indentation is happening. So that is very important. So that's what is being mentioned here. Indentation matters. So yeah, so we can start checking out some if statements. So we can check if a condition is being held and then telling the program to do something. For example, if we define this variable as 5, this x variable as 5, as always, you can pick any letter here. You can pick the initial of your name, your favorite letter. You can write anything here. So if we write any variable name here, in this case it's x, you can write if x is greater than 10, print x is greater than 10. Else, that's very important, we can write a different, like an extra statement that tells us, okay, if the previous condition and the if is not met, I want to do something else. I want to do something different. So in this case, else, print x and print the text is less or equal to 10. So if we run this, it says 5 is less than or equal to 10. Notice that what's happening here is that Python is checking the value of x in here, and it's saying, okay, if we put a 5 here, is 5 greater than 10? And it's going to be like, okay, no. So this condition is not going to happen because it's seen as false. And then it goes to the alternative condition, that is else. It's like if the previous thing is not met, do something else. And that is printing this. So that's why this is being printed. It's not that, in this case, it's not that Python knows that 5 is less or equal than 10. It's just that I knew that, so I told it in case that the x value was lower than 10, it should print that. And that's what just happened. So yeah, let me have a quick look at the chat. I guess I'm not missing anything important here. We're good, right?
Madeline is on top of these
Wonderful.
answers here, and Aparajito has joined us again. Perhaps he can start with loops when you finish up what you're doing.
Oh, sure thing.
Excellent.
Yeah, if his machine is ready and everything is ready to run, if not, if he needs a bit more time, I have no issue continuing for a bit.
Okay.
So yeah, so you can also, so you can be like, okay, this is like a very binary kind of condition checking, because we're doing like, okay, if my condition is met, do something. If not, do something else. So it seems like we only have 2 options there, but that's not true. Python, that's the case in many programming languages, but in Python there is like a specific little conditional that we can use that is called elif. That is like a contraction of else if, so that lets us add as many conditions as we want. So we can, in this case, have 3. For example, if we define x to be 10, and then we say, okay, if the value that I have is greater than 10, print something. But I want to add the other condition. Okay, if it's greater than 0 also, then also do a different thing. Or else, if none of the previous conditions are met, then we can give them the alternative request or the alternative order. So in this case, x is equal to 10. It goes in here and it checks, is x greater than 10? It's not, it's equal to 10. So it's not going to do this. It's going to go evaluate the second alternative, that is x greater than 0? It is. So it's going to go and print x is greater than 0 and less or equal to 10. And then it's going to go and check, it's going to finish there because we already met the true, and then we don't have to go into the alternative final condition that is on the else. So so yes, that's why it's printing 10 is greater than 0 and less or equal to 10, because that's what I told it to print when it met the condition of x being larger than 0. So that's the main part on that side. So now we're going to see that we can use this. It's very, very useful to run loops. we can tell Python to be like, okay, have this variable. Maybe that's a variable that changes with time. And for a specific amount of value, like for a specific value of that variable, we want to do something. But then if it changes to a different range of values that we don't care about, we can tell Python to skip those. And that's what we can do with loops. We can tell Python to go into a little cycle of running several things for an amount of variables, of numbers, of names that we want to apply a function to. So yeah. Is Aparajito catching this one here?
Absolutely. He is ready to go.
Wonderful.
Aparajito, you're good to
Okay.
continue with us, starting with loops?
Yeah. Thank you so much, Maddie and Geronimo, especially for taking over midway. I had some technical difficulties. Okay. So, you guys should be able to see my screen about now. Yes. It's visible, right?
You can see it now.
Okay. So you learn how to print stuff. You learn how to do basic mathematical operations in Python using numbers, and then you learn how to assign variables using the equal sign, which is a little bit less intuitive. If you're familiar with algebra, if you're used to algebra, and then you learn, because equal sign means something else in programming, and then you learn how to compare two values, whether or not they are equal or unequal, using Booleans and conditionals. You learned about the different kinds of collections, namely lists and tuples. So we have the little building blocks. We know how to, we know that we can put these together to make something more complex, something that's more useful, something that does, more than a basic calculator, right? We want to slowly discover the full potential of Python. And there's two ways to do that, right? One way is, and both of them involve repeating stuff. Because when you have compiled a small block of code, right, with multiple simple operations rolled into one, and to make one complex operation, you might want to repeat that, right? You might want to do that more than once. So in that case, writing that block of code over and over again seems redundant, right? It seems useless. There must be a better way. So there could be two kinds of this repetition. One would be repeating in one place. So you might want to repeat that exact same block of code multiple times in one place and then forget about it. Or you might want to bring it up again and again at different points in your script or in your notebook, right? You might want to execute it once and then do some other stuff, and then you might want to go back and execute it once again with some other output, right? So we have two different things to achieve these two effects. And the way to do the first thing is a loop, repeating in place. Sometimes you want to repeat the same series of steps many times. And for Python, the most common kind of loop is a for loop, which we'll come to in a short moment. For now, let's look at a while loop, a more simple solution, a less elegant one, but it will give us all the pieces of a loop. So we have one variable called countdown, and we have set a number here, and this will be the number of times that the loop will repeat, the loop will iterate. And then we have then we have the loop, the main body of the loop, while loop, we say while countdown is greater than 0, we are going to do something, a very simple thing in this case, which is just print the number that is countdown, and then decrease the value of countdown. So once these two steps are executed, the while loop will loop back again. And you can see that the while loop is defined by the indentation that Geronimo mentioned. We have indented with a tab. This is 4 spaces. And let's see. Let's do some line numbers. So sorry. Okay, so we defined while loop using that indentation. And that means when the indentation ends, the body of the loop ends. Okay, so everything that happens after that indentation ends will not be repeated, but everything inside that indentation will be repeated. And reminder that you can indent with anything. You can indent with a single space. You can indent with 4 spaces. You can indent with 8, 10, how many ever you want. The key is that it should be consistent. You cannot indent with a single space here and then 4 spaces after in the second line. Okay, Python will not register that as being part of the same indented block. It will register them as 2 different indented blocks, which will give you an error. Now, so what this basically does is just prints the variable countdown, the current value of the variable countdown, and then it decreases it, and then it goes back and checks if the value of the variable is greater than 0. If it is greater than 0, then it prints it again and decreases it again, and it keeps going as long as the value of that variable is positive. All right, so let's run this. So it's running. You can see that it printed 3, it printed 2, it printed 1, and then it just stopped. And then it printed liftoff. Liftoff was not printed at every iteration. Liftoff was only printed once the loop ended, right? Because it's outside the indentation. We can play around with the value of this variable. We can put in 5, and you can see that it's 5, 4, 3, 2, 1 liftoff. Okay, a simple countdown code. Okay, and the problem is that while the while loop, pun not intended, is simple, it runs into an issue. What happens if instead of greater than 0, I put in less than 0? If I keep it greater than 0 and if I increase it to +1, okay, instead of decreasing at every step, I keep increasing. What do you think will happen? It will increase it at every single step, right? And it will keep checking if the value is greater than 0. And for every single step, the value will be greater than 0, right? So there will never come a time when the loop will end until I run out of memory, right? Or rather, the computer runs out of memory. It runs out of RAM. It will not end until your computer basically gives up. So that is what's called an endless loop. And this is a problem with while loops, right? You have to be very, very careful about how you modify that variable and how the condition works, how the loop condition works. So we will not do that. We don't want to get stuck in an endless loop, but you get the gist, you get the concept. So how do we stop that, right? And for that, we have something called a for loop, okay? A for loop also loops over some values, okay? But it has a specific endpoint, okay? Let's see. So we have to find a list here. We have called it my list, and it's just a simple counting up from 0 to 3. And we're saying that for I in my list, okay, yes, as you can see, that variable I has not been defined yet. And that is, in fact, how it's used, okay? It's a placeholder variable. You can just use it in a for loop here, and for loop won't matter. And this is basically how that variable is named. What you're saying is that for I in my list, print I. For I here stands for every element in whatever collection there is here, okay? In this case, the collection is my list. So what you're saying, what you're asking Python to do is to look at every single element from that list called my list and then print it, okay? And we're going to run it. As you can see, it's 0, 1, 2, 3. I can change a value and it will change the code, right? It will change the output of the loop. Once again, it loops over every single element in that collection in sequence, right? In order. And once it has run out of values, it just stops. You cannot make a collection that's infinite, so you don't get that infinite condition with for loop. Unless you do something extremely strange and unorthodox. So this is a much safer way to loop things. And this is usually what we use. And once again, we can do the thing we did with the while loop. We can put something outside the indentation. As you can see, the all done bit, the all done line did not repeat. Everything within the list repeated. And then once that ended, once the loop ended, it printed all done, all right? And you can also nest loops. You can have loops within loops. And this is where indentation is very important. Remember what I said, indentation has to be consistent within a loop, because if you change the indentation, Python will think it's part of something else. So look at this. For I in range 2, what is range? Let's see what range is. So if I just do range like this, okay, it will give me something that looks like this. Okay, it's basically telling me that range 2 is the same as doing range 0, but it doesn't mean anything to you just yet. You can convert it into a list. Range is kind of its own data type. And you will see that basically range 2 is just like equivalent of the first 2 integers, okay? If you do range 3, it will create a collection of the first 3 integers starting from 0, okay? Just like that. Remember, Python starts indexing at 0. All indexes start at 0 for nearly all programming languages, with some notable exceptions. Basically, a range has 2 elements, a start point and an end point. So if I do 1, 3, you will see that it goes from 1 and then it stops before 3, okay? So whatever is the final endpoint, it will stop before that, okay? As you saw, I can use it with 1 input, and it will basically assume that the first, the starting point is 0. And it will basically start from 0 and stop before whatever I'm providing. So that's what's happening. 0, 1, 2, and then it stops before 3. So it stops at 2, right? Can we add a third variable? Let's see. Let me dial in 0.5. Okay, that doesn't work. Let's try 6. Okay, and do 2. Okay, this does work. So we should work with only integers. And as you can see, if you add a third variable here, sorry, a third input here, it will use that as a step. So it starts from 0. It uses, I should zoom in a little bit so that you guys can see better. Okay, this is better, I think. So it will start from 0. It will use a step of 2 to reach up to 6, but it will not reach 6. It will stop right before that. So it goes from 0 to 2, 2 to 4. And then if it wants to increase further in steps of 2, it would have to go to 6, but it can't, so it stops at 4. Okay, that's range. We're using it with a 1 input here. So you'll basically get 0 and 1. The first for loop, the outer for loop, will loop over 0 and 1. And then we have range 3. So the inner for loop will loop over 0, 1, and 2. All right. As you can see, that this is where the for loop, outer for loop is indented, and this is where the inner for loop is indented. So everything inside this first indent will be repeated as many times as the outer for loop, instructs. And everything inside the inner for loop will be repeated as many times as the inner for loop instructs. Okay, so for every single iteration of the outer for loop, the inner for loop will run completely. Okay, it will complete every single iteration of the inner for loop for one iteration of the outer for loop. Okay, and that's what you're seeing here. Outer index 0, and change this to inner index. Okay, outer index 0, inner index 0, and then keeping outer index 0, inner index increases 1, and then it goes to 2. Then it means done with outer iteration 0 because it has completed one full loop of the inner loop. All right, and like all iterations of the inner loop. And then it goes to the second index of the outer for loop. And then it prints the outer index of 1 and then every single index in inner index once again. So it goes from 0, 1 to 2. Okay, twice, once for each outer for loops indices. I hope it is sufficiently clear. If you have any questions here, please feel free to ask. I know we are, escalating the complexity here. Take a quick look at the chat. Anything else? Jamika, please shout me out if something comes up. Okay, so we just learned about loops. So that's the way to repeat some instructions multiple times in one place, all right? Oops, we have a chat. Let's see. Oh, okay. Okay, Somebody has asked, sorry, but I could not understand the third input part. So I'm guessing you're talking about range, right? So I hope you have understood the first and second inputs. The first input is the starting point. The second input is the end point. And if I just leave it like that, you will see that it goes from the first input all the way to right before the second input in increments of 1, in steps of 1, right? It will not reach 6, it will stop right before 6. It will stop 1 step before 6, okay? And it will start at the starting point, okay? So the step size is 1, the default step size is 1, just like how the default starting point is 0, okay? But we don't need a default step size. We can customize the step size. So I want a step size of 2. So we go from 0 to 2 instead of going from 0 to 1 and then 2. We go from 2 to 4 instead of going from 2 to 3 and then from 3 to 4. Okay. And then if we're going with steps of 2, we'd have reached 6. But it stops 1 step before 6. So it cannot go to 6. That's why we have 0, 2, and 4. Okay? That's what the third input does. It defines the step size. Okay. Now, we have understood loops, hopefully. That's repeating stuff in one place. If you are having trouble, please feel free to ask questions, and I highly encourage running these notebooks, running them on your own. We provide you with all the empty notebooks for this exact reason. You have to try it out. Remember that this is an interactive tutorial. Even if you're doing it asynchronously, you should do it yourself. Okay, the second way of repeating code is through a customized function. Jamika, I don't know if we are taking a halfway break, and I don't know what the time would be.
It's fine. The break is scheduled for after notebook 2. Okay. Yes, please continue. Thank you.
Okay. So the other way would be a customized function. You've already seen how functions are used, right? You've seen the print function. You've seen the length and range function. Maddie pointed this out, that the parentheses should be used very carefully, right? One way of using parentheses is to make sure that your mathematical operations are, running in the correct order, in your intended order. The other way to use parentheses is to write some kind of keyword for a function, and then open a parentheses, put some inputs in there, close the parentheses. Just like I used, there are 2 functions here. One is range, which is also its own data type, and then there's the list function, which literally converts a different data type into a list. We don't want to just work with what we have been handed. We want to make our own functions, okay? And that's where the sections comes in. That's where the def keyword comes in. So def is a statement. You can see that there's a space after the keyword. So that is a statement. We are not opening parentheses. We are using a space. It's a statement. In early Python, for example, print used to be a statement. Now it's a function. So we say def, and then we say the name of the function that we want to create. And we have to be careful to not use the name of an existing function, because that will essentially override that function. We want to come up with our own function names. So that's what we've done here. We've come up with norm, okay? And we're telling Python that the norm function will have 2 inputs, x and y, okay? You can name them anything when you are defining the function. You could name them A and B. It's okay. Just make sure that you use the same variable names inside the function. And Another thing is that the namespace of a function or like the variables within a function don't really have any connection with the outside. So once you have defined this function, you can actually use x and y elsewhere, and it won't mess with the function when it runs. We'll see that later. Don't worry, that does not make sense right away. And we are saying that we are taking two variables, x and y, and we are defining a third variable n using x and y. And how is n defined? Well, it's square of x plus square of y, all raised to the power of 0.5, 1/2. So we're taking the square root of the sum of x squared and y squared. Okay, that's what we're doing. This is how you take a square root. You just raise it to the power of 0.5 or 1/2. And once you have defined norm like that, you can just print norm, and generate a value using a set of inputs. Ta-da. So I can just, for example, change it to -3, and hopefully it won't change anything, because of course we're taking the square of y, and it didn't change anything, right? So functions define their own variable scope, like I said. We can define something a little bit more complicated using 4 inputs and using previously existing functions. So much like how we called a loop within a loop, once you have defined the function, it's available in the namespace. And that's the magic of Jupyter Notebook. Every cell knows about every other cell that was run before it. So we have already defined norm. Now we can use norm inside this function. This function will know about norm. And as you can see, distance just takes the norm of x2 minus x1 and y2 minus 1. Okay. And then you print whatever was created by that result. Shamika, you want to tell me something?
Yes, quick question.
Yes.
So there was a request to explain outer and inner iterations one more time, please.
Okay, sure. Let's go over that real quick. Okay, so what is a loop? A loop basically repeats something multiple times, right? So you can essentially repeat something multiple times within a loop, okay? Sorry, let me take a step back. Okay, so you're repeating something, but what are you repeating? Okay, the thing that you're repeating could then in turn repeat something. Okay, it's like fractals. Okay, so the outer loop repeats whatever you're doing here 2 times, okay, twice. And every time the thing that is repeating is an inner loop. That loop itself is repeating something 3 times. Okay, so the outer loop runs twice. Okay, the first time it runs, it has an index of 0. Okay, we know range 2 would start as 0 and stop at 1. So while the outer index is 0, okay, while I is 0, the inner index, okay, will change 3 times. This entire loop will run. Okay, nothing is stopping from this entire loop from running. Do you know why? Because it's indented. Sorry, yes, it's indented as a new loop. It's not indented within the outer loop. This line will only repeat twice. Okay, this line, this last line is not a part of the inner loop. This line is a part of the outer loop. so it's repeated twice, all right? But the inner loop, it's not limited how many times the inner loop runs. It's not affected by the stuff that's outside this indentation, okay? It's only defined by this number here, okay? And that's why it runs 3 times for every iteration of the outer loop. So the outer loop, it runs once, okay? The first time it runs, it has the index of 0. The inner loop runs the first time. First iteration of first iteration of outer loop, first iteration of inner loop, it gives us this line. First iteration of outer loop, second iteration of inner loop, it gives us this line. First iteration of outer loop, third iteration of inner loop, it gives us this line. And then it ends, then the inner loop stops, okay, for the first time. Then the outer loop runs again. Second iteration of this outer loop, first iteration of the inner loop, second iteration of the outer loop, second iteration of the inner loop, and so on, okay? I hope I didn't mix up my words there anywhere, but I hope you get the gist. Try it yourself, change the indentations, see how it affects your code, add some lines, add some basic arithmetic, try operating with I. You can actually try operating with I, see if it messes up the loop, see if you get something interesting, experiment. Encourage you to do that. Shamika, do you think that was okay?
Yes, thank you. The responses, that was very helpful. Thank you so much.
Okay. So back to distance. We know what norm does. It sums up the squares and then it takes the square root of that sum. And distance is a second user-defined function, defined using the norm function. So it defines a variable called dist, and then it prints that variable dist, and then it returns that value dist. All functions should have return value, and if it doesn't, you should add a return none. None is kind of like the empty nothing variable. So yeah, just keep the structure intact. I encourage that. So we have defined distance, and then we say result is distance this, and then we print result. And if I run this, you'll see that result is defined using distance, and at the same time, the function will print the value of distance using dist equals, okay? Dist equals value. And then this line, print result, will actually print it again, print the return value, which just so happens to be the same thing. I can change this, for example, and say print dist plus 1 and then return dist. That will change the first print output of the first print thing, that thing inside the function, but it won't change the output of this. Let's verify. Yes, it added 1 to the print that happens inside the function, but it returned the same value, which was dist. So this print did not change. Right. So once again, once we have defined the variable, defined the function, the rest of the notebook knows about it. We have said dist. Now if we assign a value to the outside the function, it won't be changed by the function. Like I said, functions have their own namespace. So if you used a variable within a function while defining a function, right? And then you use it somewhere else, it does not affect the function. Okay, that's the magic of it. functions kind of have their own namespace. So you can see that we have used the variable dist, right, while defining the function. So what happens if you reassign something to dist? We recycle that variable name. Does that affect the function? And the answer is no. You can do dist equals this to reassign that variable that you used to define the function. Then you can test the function again by running it again. And then you can print the output of the function, which is result. It should be result. Oh, yeah, I get it. So result, once the function is running, it will print dist, okay? And you'll see that it is the correct thing, okay? Because this first line is printed from within the function. Because when the function is running, the function thinks dist is whatever it knows within its namespace. And what the dist that is knows with its namespace is defined by norm. So it prints this number. But the dist that the rest of the notebook knows, okay, outside that function is this one, outside variable. So when you use the print function after that, this is what you get. So you have two different dists, one inside the function and one outside, okay? Functions have their own namespace. And you can actually try to mess with this using some keywords, but that's advanced stuff that we won't get into today. Again, we can actually define functions without any inputs. So as many inputs as we want, 1, 2, 3, 4 are in fact 0. So this, for example, always defines the exact same list. You know, you might not need this function, but certainly not a very useful function. But yeah, you can do this. There are other things that you can use this feature for. Sometimes you do need to define a function without an input variable. It's not very common, but you can do it. I make a list, and it will simply give you this exact same list every single time. Okay, it returns 1, 2, 3, assigns it to y when you run the function without an input, and then when you print y, you get the list that you defined every single time. Define double a list. Now this takes a list and then it doubles it. Doubles every single element in that list, okay? Instead of, you know, just making it twice as long. So if you input 1 and 2, it will define a new list. It will define a new list that's where every single element is reassigned as twice of what the input variables element was, okay? And in this case, it just writes over the list. As you can see, it takes x as the input, and then it literally just redefines x, redefines every single element in x. It loops over the length of x, loops over the range of length of x, and for every single index of x, it doubles it, and then it reassigns that element in x. So you can define a list, x equals 1, 2, and then you can just run the notebook, run the function on its own without assigning it to any value. And then if you print x, you'll see that it has doubled because the function has literally taken it in, and then it has forcefully changed every single element in the input, okay? This is like the biggest function in this notebook. Do we need to go into this? Raja, Jamika, or should we move on to the next things? Corners of the rectangle, this function takes some time. Can you guys hear me?
Yes, yes.
Yes. You can hear me, right?
Yes, all good.
Yes.
Yeah. Okay. Should I go over the function, or do you want to move over to the next section?
I think we should move on only because we're definitely over
Yeah.
time here.
Exactly. I know.
But thank you.
We have importing other modules, but we do that in notebook too. Okay, I'll stop screen sharing and look at the questions that people have.
Pargito, thank you. Thank you, Madeline. Thank you, Geronimo. Thank you, Raja. It's been great. There's lots going on in the chat here, so yes.
All right, should we go ahead and take our break now, Jamika, and then go into the next
Please join
segment?
us back there. No, let's just move ahead. We're pretty far behind on our schedule.
All right.
Please.
So I think I'm up next. We're
Yes.
going to let me double check this. All right. We're going to quickly go through the structure of an astrophysics journal. Can everyone see my screen?
Yes.
Okay. All right. So we're going to move a little more quickly than we usually would, but this is a resource that is in the documentation you all have, and I would encourage you to read it in more detail. But the most important things on the first page are going to be your title. This is going to be something really fancy and intimidating sounding, but the more science you know, the more you're able to pick apart what exactly is going to be in this paper and whether or not it's interesting based on the question you're trying to answer. Then you have your list of all your collaborators. The amazing thing about science in the modern day is it's not, all one great scientist. It's hundreds of great scientists working together. And from there, we can move on to information like knowing when it was published. That can be important because it could be a newer result that you are more interested in, but sometimes classic results are still interesting. So don't just dismiss something because it was written in, the 80s. Our abstract is a summary of what you're going to read in this paper. It should include the scientific context, so what's going on, why they're trying to answer this question, what the main points of the article are, and then what results and conclusions they found. In your introduction, which is this first section here, a good introduction should give you a little introduction to the scientific background. So what is the problem that they're trying to answer? The motivation is why do we care? In this case, you can read about why they care here, identified by the numbers. And then 3, they'll give you a preview, a quick summary of what they did and what they're going to cover in the paper. There are some sections to this paper that aren't in other types of papers because this paper is about observing Andromeda galaxy. It has a section about how they got that data and how they sort of cleaned it up scientifically. Others may have what's called a methods section, which is just specifying what you did and why. A really important thing about these papers, whether you're writing one or reading one, is that they should include enough details someone who's reading it can replicate your results. That is one of the most important parts of science, is that we're able to replicate our results so that others can test it and so that we're being transparent about what we're doing. So they do have a methods section here. That's where we'd read about what they did. Now, one of the secrets of reading a scientific paper is that once you know enough about a certain subject, you can actually just skip a lot of that and move straight to the figures, as they're called. We call these figures, not pictures, because they can be plots as well, meaning graphs, as well as like images like this one. This is one of the most important parts of a paper because someone should be able to tell exactly what's going on in your paper just from looking at your figures and the caption. Now, I'm going to highlight some things about this figure that we're going to use in the next couple of sections. One important thing about any figure is that you give it units and a label. If you're making a plot, you don't want to just have one axis be called X and the other one Y. Because what is X? Is it time? Is it distance? Is it something like that? You need to clearly label what they are and what units they're in. Say it is distance. The distance between, or the difference between a meter and a kilometer is a huge difference. And so that's going to make a very big difference on how someone interprets your plot. You give information on what is in your figure down here, including specifying what all the colors and shapes mean. And in this case, we'll use very similar values here on our X and Y axes when we're plotting up our stars later. And these are just coordinates on the sky. We'll talk a little bit more about what they mean later. You can think of it like longitude and latitude, basically. Now, equations are the other essential part of a paper. That's the other thing you can skip and scroll to just to figure out what's going on. Equations are always set on separate lines, and they're numbered for reference so that later on you can say, oh, as equation 1 says, you know, we're gonna do this. All right, we'll learn more about what spectra mean, but this is an example of a spectrum, and as you can see, they have very large, very clear axes that are labeled with units. Right, keep scrolling past our figures, past them explaining what is in those figures and how they made them. And then we're going to move to the results section. Now, results, the methods is what you did, and the results is what you found out. A results section should explain what it means that you found what you did, though sometimes it's also called a discussion section, just a nuance. But results is, you know, what you found in your investigation. Keep scrolling. So the discussion, this paper does have a discussion section, not every paper does, is like, so what does it mean that you found out that, you know, all caterpillars are 3 centimeters long? Like, so what is the significance of what you found? Why does it matter? And especially, how does your findings fit in or compare to other works on the topic? Say every caterpillar ever has been measured to be 5 centimeters long, then it's significant that your caterpillars are 3 centimeters long, and you want to discuss why that is. Discussions can be quite long, as you've seen, because you want to discuss all the implications of what you found. And then, just like any good 5-paragraph essay, you're going to have a conclusion. And a conclusion should summarize your findings and the important takeaways, and can be a place for you to discuss future work. Also, really important is this acknowledgement section where you want to thank who funded you, people who really helped, and people who reviewed your paper, just to, you know, acknowledge that science is a very collaborative effort, and so that you're transparent about where your money is coming from. References. This is absolutely essential, not only because it's the right thing to do to recognize people for their work when you reference it, just like your citations in an essay. You really, 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 really want to give yourself more credibility by saying, look, here is my references to existing works that everyone respects. Or, you know, oh, here's where I got this idea from, so someone else can go read the original source of material and see what they think about it. So this is a quick little test of what do we cite. I'm going to give you 2 examples. The first example is the phrase, the sun is about 5,700 degrees Kelvin. Do you think you have to cite that? The answer here is probably no. This is what's known as a commonly known something. It's a fact that everyone can pretty much agree on. So you don't need to cite something like a simple statement of fact, like the sun is about 5,700 degrees Kelvin. Now, what about the statement, The temperature of the young sun was insufficient for liquid water to be present on early Earth, despite evidence that liquid water was present. We indeed do want to cite that phrase because it's a controversial thing or something that is still being studied, or it's a statement where someone may not immediately know or agree or know where you got that information from. And then last and not least, you have an appendix section that is made up of any of the extra figures and tables that aren't important but help you tell your story or that people would find especially interesting. All right. With that, I encourage you all to go read through this. You may not be able to be familiar with the exact word that they're using in this paper, but you can definitely at least read the abstract and the first couple paragraphs of the introduction to get an idea, because we'll be talking a lot about these scientific concepts later. All right, we're moving into this notebook here. Now we've talked about how to do our basic maths, manipulate lists, manipulate strings, add integers, assign variables. So now we're going to employ a couple of convenient tools that are already built into Python. So we're going to follow this tutorial to learn how to import packages. Now, packages are external sources of different sort of Pythonic tools. So one famous one is NumPy, which we're going to use this statement import to import the package. And we're going to give it an easier name than NumPy. We're going to call it NP. So every time we want to reference the NumPy packages and the tools and functions that come with it, we're going to use NP instead of having to type out NumPy. And the same for matplotlib. Matplotlib is a plotting tool. It's going to make our job really easy when we're plotting up our scientific results. And we're going to use this same phrasing, import matplotlib.pyplot, that means a function inside matplotlib, and we're going to give a simpler name, we're going to call it PLT. These are pretty industry standard. And almost any notebook you run, you're going to want to import these two things so that you can do some basic functions. This last line is something that's specific to Jupyter Notebook. This just allows you in older versions of Jupyter to always have your plots show up in this same notebook and not as a pop-up. So let's run these things. Okay, so now we should have NumPy imported. But actually, I want to test and show you something first. I'm going to restart my kernel so that it clears out all the variables and imports that I did. And I'm going to, excuse me, I'm going to try to run something. I'm going to use np, that's numpy, let's use the nomenclature we're going to use below, 100, 0.5. I'll explain what this means in a minute. Let's try to run it. Oh, dang it, apparently I didn't clear my restart. Oh, drat, guys. I can't demonstrate this to you because I've done something to my notebooks where I have them automatically import NumPy and matplotlib. But if you try this for yourself by typing this or by running the next section without importing NumPy and matplotlib, you'll get an error where it says, I don't know what an NP is. What's that? That's how you know that you haven't imported what you need to. So I import these. And then let's go to work. Let's start using these packages and their
Maddie,
tools.
do you also have PLT predefined?
Yeah, I do.
Okay, okay.
See, when you do this enough, guys, you really get tired of typing this at the top of every notebook, and so you can do some tricky things to make them show up in every notebook without typing them. That's what I did.
You can probably change the input NumPy to something else, input NumPy as n or something, and show them that.
And then we'll see that it doesn't run. Yeah, that's a great suggestion, Alvarito. For sake of time, I think I'm just going to keep scrolling. But if anyone wants to test that for themselves, just run it without importing NP and you'll see that it breaks. Okay, so we spent a long time thinking about lists, and lists are distinct from what we call arrays. Arrays are a collection of numbers. I don't want to say a list of numbers because a list is something different in Python. That we can actually use similar queues as we did for lists in order to generate these arrays of numbers. So I'm going to use the tool of NumPy, or the package of NumPy, and I'm going to call on one of the functions that's inside of NumPy. It's an automatic function that just comes with NumPy, and it's called arange. Now, this is different than the word arrange, which has two R's. This is a array range, an array with a range. So don't go typing two R's, it won't work. And we're going to start just like we did in our list, start at 0, go up to 100, and we're going to take step sizes of 0.5. So we're going to print this out, and we're going to use our same mixture of strings and variables to get information about this. We're going to decide what is our length of this array, what is the mean, so the average of that or values in that array, what is the maximum value in the array, and what is the minimum value in the array. Now, I will say there are built-in Python functions where you don't have to import anything and you could run max just like that. But we're going to focus on using the NumPy tool max. So when I execute this cell, indeed I get a printout of that whole long array, stepping in steps of 0.5 all the way up to, but not including 100. My array is 200 values long. It has a mean of 49.75, a maximum of 99.5, and a minimum of 0. And we can sanity check ourselves by saying, oh, look, yep, the highest value in this array when we printed out is 99.5, and the lowest value is indeed 0. So let's see how we can change our array. I mean, I would suggest in your free time, go change these values, mess around with them, see if you can make an array shorter or longer, has a different step size. That's how you get a feel for these things. That's how you get mastery over these things, is just playing. Just play around and see what happens. All right, so what if we want to do some math with this? Fortunately, NumPy comes with some fancier math than just, plus and minus and power. We can do things like sines and cosines. We have our array x, and we're putting that in as the argument. I'm going to make a note here that if I were to do this with a list, it wouldn't work. We need to do this with an array. Okay, so we've defined now a variable called y1 as being the output of this math function, the sine of x divided by 10, and y2 is being the cosine of x divided by 10. But it's kind of meaningless to me. I don't actually know what these are going to look like. So we're going to make a figure, just like we saw in the scientific paper. We're going to plot up our function to see what the output is. So unfortunately, this is already shown. I guess I should clear this notebook as well, but we're just going to keep rolling through it. So what I want to do when I'm making this plot, I'm going back on my words. I think that it's important to me that we are able to guess together and see the outputs. So I'm re-executing these because I cleared the outputs so we can see them again. Ta-da. Okay. All right, so now we're going to make a figure of this. So we're going to use that matplotlib.pyplot that we imported as the abbreviated, much more convenient PLT. So we're going to do plt.plot. That's calling a function called plot. And we're going to, just like you would when you're you may be making a plot by hand, we're going to have our x values, so how far you're on the x-axis, and y values, how far you're on the y-axis. But we're not just going to plot those willy-nilly. In fact, let me do that. I'm just going to comment out the rest of this. Oh, no. I'm going to comment this out, and we're going to plot this. Just that. Oh. Okay. This means nothing to me. I don't know what my x values are. I don't know what my y values are. I don't even know what line I'm plotting. So we're going to go in and we're going to add some more helpful information. We're going to add a label. And whenever you make a label, you have to do this function as well called legend. If you don't, it won't show up. So we're going to leave it commented out, and we're going to see that it doesn't show up. We're going to set a color. I want this one specifically to be magenta. I'm going to set the width of my line. Right now it's defaulted to 1. We're going to make it a little thicker so it's easier to see, and we're going to make it a dashed line. Okay, now we're going to plot our second value, y2. We shared the same x array as our x-axis, and so we're going to plot those on the same plot because we can overplot them. They share an x-axis. And we're going to do the same thing. Label it, give it a color, give it a line width. In this case, we're not making it a dashed line. It's going to be a solid line. Okay, let's see what happens if I don't change those ranges. Okay, so I have a plot now from 0 to 100. But what if I wanted to zoom in a little bit or zoom out a little bit? What I can do is I can change the limits on either axis. So right now I'm going to change the limits on the y-axis. So right now it goes from -1 to 1. Let's make it go from -2 to 2. Okay, we've zoomed out a little bit. Now our y-axis is from 2 to -2, just like we specified here. And you can do the same thing for the x-axis, plt.xlim, and I can make it, I don't know, from 10 to 60. And we'll see we zoom in there. I'm going to get rid of that just so it looks the same as everyone else's. Okay, but I still don't know what line is which. I mean, I could look up here and be like, okay, yeah, I remember I made magenta sign. But it's way easier if I have a legend. So remember we have to do the plt.legend. Cool. Okay, so now I can look immediately at this and tell, okay, dashed magenta line is sine and solid blue line is cosine. But still, what are we plotting over? I don't know. What is our x and y axis? Well, let's give them labels. We're going to, sorry, I keep scrolling a little too much. We're going to make an x label and give it a string of whatever we want to call it. I could call it, I don't know, dogs or whatever my x-axis is. And when we execute, we're going to get those labels here that tell us what they are. Change that back to x. Okay, so now we've made a plot. So what if we didn't want to just use sine and cosine? What if we wanted to use something else? Let's make a new x array. So this array, what is it going to do? It's going to start at 0. It's going to go up to 1. And it's going to take step sizes of 0.01. And let's make some new functions. Let's see what happens when we plot x to the, what is this? X to the third power, x to the 1/2 power, and 2 times x minus x squared. And notice how we give each of these a different variable name. If we called them all y, then we would just rewrite y and overwrite what we had had before. So we want to keep these as separate variable names so we can plot them up. So same thing, plt.plot, and we're putting our x array and our output y array, and we're going to set some things about it, including what they're called. Notice that here we're using a notation in which we use these dollar signs with an R before, specifically with an R before your string, mean that it'll put it in a format where it uses what's called latex notation, and it'll make it so that you can, yes. I saw a raised hand.
Yes, that's me. Claire mentioned that she's been following along, but she wasn't able to create the plot. Could you review that quickly?
Absolutely. I don't know how to get this floating thing to go away now. Well, yes, there we are. Apologies, folks. Hang on. I just got to get this out of the way so I can see what I'm doing. Okay. All right. So we've made our plot up here. To review what we did, we created an array from 0 up to 100 in steps of 0.5. We said, what if we did some math on that array? What if we tried to learn what happens when we divide by 10 and take the sign of it? That's our y1, and then the cosine is our y2 value. So this is an input, x, and y is our output. And then here we use the matplotlib PLT, and then we call the function plot. We make an X and a Y. This should all be in your notebook already, so you can just execute it. I'm just reviewing what these things do. And then our label is whatever we want it to be. In this case, we're going to remind ourselves that what we did is sign, set a color, set a line width, set whether or not we want it to be dashed, solid, etc. And then we can set our limits on our either axis. We can say our y-axis or our x-axis. We can zoom in, zoom out, limit how much we're seeing or the range over which we're plotting. You have to have this plt.legend so that this legend will show up. And we want to always, always, always label our axes, especially with units if units are relevant. And so when you execute this cell, if you have executed everything up above here, including importing them, defining our array, and doing a math function on that array and assigning that to a variable called y1 and y2, we should then be able to plot what y1 and y2 are as a function of x. Okay.
Thank you, Madeline.
Yeah, absolutely. And so feel free to review these things in your own time too. And there are folks in the chat who can hopefully help you resolve it if you're having a computer issue with it. Okay, so let's mess around and do some more math. We're defining our array from 0 up to 1 in steps of 0.01. To jump back, we're going to do define y2, y3, y4 as 3 different functions performed on x, and we're going to plot those up. We want to remind ourselves what is what, and so we're going to use a label. And the LaTeX form of these means that we're going to get this in a prettily printed math output instead of getting caret, curly bracket, slash, whatever. So we'll see how that comes out. But to do that, you must have the R and you must have everything that is mathy enclosed in these dollar signs. Okay, so we're set a legend as well, but we don't like, say we hated our legend being up here in the right corner. We can actually control where our legend goes. You can do this by putting a number, or you can even write it out in English using one of the valid inputs like upper left. Set the font size, and then place your X and Y labels as well. Okay. So we can see that we did not define colors of what our colors are going to be. That's okay. Matplotlib will just cycle through the automatic colors it uses, which is always blue first, then orange, then green. But we know what each of these is because we've made a legend with labels. And if I were to change this back to 0, which is what you all have in yours, we can see it shows up the same place. So you can specify where your legend goes. Okay, so Google always is your friend. I would recommend going to Google first, not to ChatGPT first. Go to Google first, learn how to use Stack Exchange. It's going to make you a better coder, and it's going to mean that our planet doesn't die as quickly from the emissions of how costly it is to use large language learning models. Okay, so we are now going to oh no, Aparajito, I'm so sorry. You were supposed to do functions and figures. I'm moving quickly. Do you want to do the notebook 3 then?
Yeah, I'll be happy to.
Sounds good. Okay, so Aparajito's going to take us to notebook 3. But before we do that, we are going to break, Jamika, or do the slides?
Yes. Let's go ahead and do that for 5 minutes. There's several questions that are being answered in the chat right now, so that'll give you and Parajito, Geronimo, Raja a chance to answer those questions. Thank you all so much. Thank you, Madeline. This has been really fantastic. And thank you all again for your understanding about the issues with Slack. We'll definitely attempt to troubleshoot that. In the meantime, putting your questions here in the chat has been great. And I appreciate the responses that you are giving back to us in regards to the feedback from Geronimo and Madeline and Parajito. So thank you. We'll start again at 7 minutes past Sorry, 9, 10, 11, 12. That's be 12:27, 12:27 in 5 minutes. And
Wonderful.
I will
Okay.
come back on. I'll come back on and say, okay, we're ready to start. And then Aparajita will lead us through notebook 3. Woo. All right.
We can take this, we can use this break to answer a couple of questions. So a lot of people seem to have the issue of the plots not showing up. This is a little bit of a version issue, and it kind of varies depending on the architecture of your system, maybe. Please add blt.show, open parenthesis, close parentheses, at the end of your code, at the end of every single block with plots. Yeah. Thank you, Maddie. Yeah, exactly like that. If this doesn't work, please get back to us. blt.show. It just asks to show the current figure. That's it. Make sure you add it at the end. And you have to add it for every single cell that creates an output. That creates a figure output. So, yeah.
Did
Great.
I
And it
type
looks
that
like,
correctly in the chat?
yes. And it looks like people have, at least one person said that they were able to fix it using that. Excellent.
Okay. If you are following along with your notebooks, that's great. That is how the tutorial was intended. But we have kept this very open-ended. If you don't have Anaconda installed right now, and you're watching this, following along, without the notebooks, if you're just trying to understand it, I highly, highly recommend downloading Anaconda later and then repeating these steps. The recordings will be made available very soon. Know how I could fix that. Okay, somebody asked, sorry, I've tried putting in blt.show, but I've been getting a value error. Do you know how I could fix this?
So that actually happened to me too. Remember how we changed what x is down here to be a different length of array than it was up here? So if you're getting the value error on the blue and pink plot, then go back up to the top, re-execute this, so we're defining x to be this array instead of the array it was further down. Re-execute that. And does that fix your problem?
Yes, Lucy.
That by the great, that fixed the problem. Okay, great. Thank you for asking that question, and thank you, Maddie, for figuring it out, because that's a nice little demonstration of how Jupyter notebooks work. It totally depends on the order of the order in which you run the cells, and not the order in which they are written. So if you run a cell that's further down first, and then you go back to a previous cell, your previous cell will use the values defined in the latest cell. So yeah, be careful about that. Sometimes you just have to go back and rerun some cells to fix that issue. And back to what I was saying, please make sure that you follow along at a later time. If you're not following along now, you can ask your questions in the Slack channel if you're able to join that. If you could not, that's okay. We are trying to answer your questions in Zoom chat. And try Googling your question. Try Googling your question if you really can't figure it out. Stack Overflow is always your friend. Like Maddie said, please don't run to LLMs first because they will hallucinate. There's a very high likelihood. Listen to people who are very experienced. Somebody has had the exact same problem before you, I assure you, and they figured it out. So find them through Stack Overflow. You don't have to depend on LLM right away. Yeah, okay, Maddie, over to you.
Thanks so much, Aparajito. An amazing overview. We're going to jump into some science first to give ourselves context to what we're going to do next. This is stars in all their glory. So let's think about how we describe stars. I usually do this as a call and response, having folks paste their guesses in the chat, but let's keep the chat stream focused on coding questions for now because we're having issues with Slack. So just in your head or in your room, shout out what you think. So how do we describe stars? Think about a star, like what attributes does it have? What can we measure about it? Well, if you said how hot it is, definitely. How far it is another attribute we can measure. How big it is. How bright a star is. What color it is. So what do these correspond to in terms of like scientific units or values? Well, how hot it is, we describe it as its temperature, which has the units of Kelvin. Distance is has various units, but for this investigation, we're going to be using parsecs, which is not just a thing you've heard in Star Wars, maybe. It's actually a unit of distance. R radius is going to be measured in meters, so that's the radius of your star. You can also, when you think about big, because when we say big, we could mean either how massive it is or what size it is. So that can also refer to the mass, which we're going to use the units of solar masses or kilograms, where solar masses are how many times larger or smaller it is than the sun. So 2 solar masses is 2 times more massive than the sun, or just kilograms. How bright does it look? That's a really tricky measurement that we're going to learn how to describe. But the unit we use in astronomy is called magnitude, which is big M or little m. And the units are magnitudes. How much energy does it give off is yet another thing we might not have thought of initially, which is its luminosity. And we do that either in how many times it is the solar luminosity, so units of solar luminosities, or in watts, which you may have heard of like a 60-watt light bulb or something like that. And color. Well, the scientific value of color is just called color. That is also something we'll learn how to scientifically define from the units of magnitudes. So what is magnitude? So the ancient Greeks, among many early scientists, looked at the night sky, and the Greeks in particular said, huh, I kind of noticed that like that star is maybe like 2 times brighter than another star, and maybe that star is half as bright as another star. And so an early Greek astronomer came up with a system of magnitudes in which he classified everything into, and Raja knows more about this person's name. You can post the name. I forget his name right now, Raja. He classified all the stars in the sky into these magnitudes. Where back then, with a naked eye, they could only see maybe 2 or 3 magnitudes of stars. Today, we can see many more. And here's the thing. It's actually a trick of our eyes. One star looking twice as bright as another isn't actually twice as bright. It is, in fact, probably a power of 10 brighter or more. Because our eyes are designed, well, our eyes evolved to work with all the light that comes through our atmosphere. And so if we could only see a very small range of light, we'd miss out on a lot of information. We couldn't go from looking outside at a sunny day to being in a dark room and still able to see. And that's because our eyes see in what's called a log scale. So it sees in powers of 10. So something that looks twice, a light bulb that looks twice as bright to us is in fact 10 times brighter. Oh, wait, that's back. So the weird thing about the magnitude system, besides it being a log scale, is that it's not only that negative numbers are brighter, where a negative 10 star is brighter than a 10 magnitude star. It's also that every unit along here doesn't necessarily mean that this is 10 times dimmer, 10 times dimmer, 10 times dimmer. It's actually a factor of 2.5. So if I go from negative 10 to negative 7.5, that is 10 times dimmer. And if I jump here to negative 5, that is 10 times dimmer, and so on and so forth. So not only is that tricky because it's negative, so it's the opposite of what we oftentimes think with bigger numbers being brighter, it's also a log scale, and it's not a log scale of just one unit equals a factor of 10. It's every unit of 2.5 is a factor of 10. Add to that the fact that as you get further away from a light source, it gets dimmer. So we have two measures of magnitude. The apparent magnitude is how bright something looks when you're standing on Earth. So a star that is further away will look dimmer than a star that is right here, that's exactly the same, right next to us. However, it gets tricky, and we use a unit called absolute magnitude because what if the stars that are, close to us and far away from us are not the same, but in fact, a star that is very far away is super bright, and so it actually looks to us like it's the same magnitude as a dim star that is closer. So we use what's called absolute magnitude to break that degeneracy, to make it so that we can tell how bright a star actually is in absolute terms. So we imagine for absolute magnitude that we're standing exactly 10 parsecs away, then standing 10 parsecs away, how bright would that star be? So that it's not affected by how far it is from Earth. Color. Color is also a really interesting measurement that is unique to astronomy. So, wavelengths of light is something you all may or not be familiar with when we say the word wavelengths, but you're definitely familiar with it in terms of the rainbow, where a shorter wavelength of light is bluer, like the red Roy G. Biv, where red is shorter. So you have a longer wavelength of, or sorry, a longer wavelength of light is red, orange, yellow, green, blue. So blue is short, red is long. And we classify these as different bands. And we give them names like R is reddish. And when we look at a star using a filter that filters out all wavelengths of light except for the ones in this, say, the green range here, V, and we look at how bright it appears, it may appear to be a different brightness than, say, it would at longer wavelengths. And we'll see why that is in a second. But what we're going to do is blocking out all of the other things and just measuring the magnitude here and the magnitude here. We're going to subtract those values, and that quantity is going to be what's called our color. Now, this is confusing, not only because I'm getting a little tired and my explanation isn't as sharp as it usually is, but it's just a confusing concept. It will get clearer when we play with these values. So our color is V minus I in this case. So the magnitude in the V band, the magnitude in the I band. And the thing to remember is that when this value is smaller, your star is, quote, bluer. Maybe not to your eye, but scientifically, the value of color, it's bluer. And when your magnitude in the V band minus your magnitude in the I band is larger, your star is redder. And we're going to figure out why these colors of stars matter. And it's actually something to do with their properties. So let's take a zoom out to understand why it is that this can be informative. So in our top panel here, this is the different bands for a specific telescope called the Sloan Digital Sky Survey. It's a space telescope. And the way that that space telescope defines these bands is it says, okay, everything from like, I don't know, 5,500 to 7,000 is the red band. And so it can measure that to get the magnitude in the red band to see how bright that star is. So now let's just drop straight down from here. in the red band. Watch my cursor as it goes. Well, first, let's look at this green line. This green line is the sun. The sun is sort of medium bright in the red band. But let's look at the star Vega, the blue line. Vega is much dimmer in the red band. And if we were to calculate the color of these, subtracting the value in one band from the value in another, the magnitude in one band and from the magnitude in another band, we'd see that, if we did, let's do something really obvious like the Z, we'd see that, oh wow, the sun is brighter in this magnitude and Vega is much dimmer in this magnitude. But maybe if we do, U, Vega is much brighter and the sun is much dimmer. And so these are going to tell us things about the properties of these stars, because not every star has the same amount of flux, the same amount of brightness coming at every wavelength. And this spectrum, as it's called, of the star, where we measure the amount of flux, the amount of brightness coming in each wavelength of light, tells us a lot about the star's properties, including what's going on inside of it, how bright it is, how hot it is, what it's made up of, etc. So this is a very busy plot. There's a lot of things going on, but I've highlighted the two things I want us to focus on. These bands here, F18W and F475W, are going to be the two bands, the two wavelength ranges that we're going to have observations in when we do our next notebook. So this is for the Hubble Space Telescope. Very famous telescope, nearing the end of its life, but pretty much every beautiful picture you've seen pre-James Webb Space Telescope was from Hubble. It's just absolutely revolutionized our understanding of the universe, and one of the ways in which it's done it is by being able to measure the spectra of things in these different wavelength bands. So we're going to be focusing on this one, the green one, which is from about 7,000 to looks like about maybe 9,000 and wavelengths in angstroms, and then the blue band, which is about 4,000 to say 5,800 angstroms in wavelength. So a Hertzsprung-Russell diagram is a way of plotting up all the stars that are in the sky, all the observed stars. And when we plot them on this plot, and I'll explain the units in a minute, it actually tells us something about the stars' histories and their lifetimes. So let's look at our y-axis first, because it's a little easier. Our y-axis here is luminosity, so how bright it is in solar units. So remember solar luminosities, if it's one solar luminosity, it's the exact same brightness as our sun, or luminosity as our sun. And if I go over, yep, there's our sun. 10 times brighter than our sun, 100 times brighter, 1,000 times brighter, and dimmer down here. Now, let's look at this x-axis. So our x-axis is temperature. And we can also use with color. But notice that it's going in the opposite direction to the way you normally plot temperature. Normally you plot increasing x values going to the right. But here we go from 3,000 to 6,000 to 10,000 to 30,000, and it increases this way to the left. So what can we tell from this? Well, there's a couple trends that we can see right off the bat. The first is that if you have a very, very bright star, it tends to be, oh look, very hot. If you have a very, very dim star down here, we can slide on over till we hit some stars and oh wow, they're really cool. And we can also see from this color down here that the color of the star changes. But what does this mean for these different groups? Were these stars just like born, bam, in each of these categories and they live out their lives there and die? Well, no. This is actually a sequence of a lifetime. That's not a helpful statement. Let me rephrase that. This is actually tracing the lifetime of these stars. So our sun, we'll watch in a second, throughout its lifetime, it may be born somewhere around here, but as it evolves, it's going to get a little brighter and a little hotter until eventually it swings over and becomes a giant star here, where it becomes very dim but very large, or very bright. Or sorry, very cool but very bright. This is much easier to see than me indicating with my mouse through this animation. So this is a star of 1 solar mass, a star just like our sun. So it's going to start out over here. It's going to move on to that main sequence. It's going to get a little bit brighter, a little bit hotter, and then as it turns into a red giant and is no longer able to fuse hydrogen and helium, it's going to become much down here colder, but brighter until it becomes a white dwarf in its last category. So that's it, tracing it over its lifetime. A star of 10 solar masses is actually going to live a very different life. Look, it starts higher up here than our sun did on the main sequence, which is where the majority of the stars live for a lot of their lifetime. And look, it bounces over, it becomes bigger, it becomes brighter, it becomes cooler, until it actually goes off the map. It's not going to end up being a white dwarf, it's going to go to be a neutron star and potentially also a black hole. So where you are on this Hertzsprung-Russell diagram indicates where you are in your lifetime, and potentially where you're going to end up. Whether you're going to end up as part of this population of supergiants or of white dwarfs, or go off the map and become a neutron star and a black hole. So what does this all have to do with color? We kind of saw the influence of color here. Just with our eyes, we can pick out that there are patterns in sort of what color you are based on what temperature you are. What about the scientific value of color? The one we talked about where we were like, okay, you measure the magnitude in one wavelength of light and the magnitude in another wavelength band, and you subtract those two to get the color, quote unquote, color. Well, we can actually reproduce the Hertzsprung-Russell for ourselves using color as one of our axes. So we're not going to use temperature explicitly. It's a proxy for temperature, though not directly the same. And we're going to make this plot for ourselves. We're going to take our V minus I magnitude, so our color here on the x-axis, and our y-axis is going to be magnitude, so how bright they are. And it may not look exactly like it, but this is still a version of the Hertzsprung-Russell diagram where we have our main sequence of stars and our population of red giants and other stars that are at different points in their evolution based on their mass. So stars, to review. Oh wait, we're not going to do this. Let's, for the sake of time, move on from this. We're going to go into notebook 3 with the PyaR. And we might just make it. Might.
Thank you.
It's okay. Thank you, Maddie. That was a really impressive 3-section run.
It was.
Yeah.
And I was going to say that even if you just get started on notebook 3, we can finish
exactly.
it up tomorrow.
That's all I'll try to do. We'll get through, as much as we can.
I'm going to run off, you guys, but good luck with the rest, and I'll join tomorrow. Take care.
Thank you, Raja.
Thanks, Raja.
Thank you.
Okay, so we learned what color magnitude diagrams are, and we learned what color is, which is a different thing from the standard use of color, from the standard concept of color in everyday life. Astronomers use the word color in a very different way. So we are going to make some of those color magnitude diagrams that work as substitutes for PHAT diagrams. And we have a bunch of data in that folder that you downloaded from the Jupyter note along with the Jupyter notebooks. And that data contains the names of some targets, the magnitudes in in 3 different filters, or 4, I forgot, and their coordinates in the sky. Okay, and we're going to use the magnitudes to create a color magnitude diagram. So we start by importing stuff. This is notebook number 3 of the tutorial. And as you can see, we imported matplotlib itself, not just the pyplot module, but the entirety of matplotlib as MPL. And we're setting some global parameters to specify how the fonts should look like on the figures, because we're going to make some, really cool figures. Let's turn on line numbers. We define something called initialize float. This basically creates a new figure and it clears the figure. Okay, sorry, it doesn't create a new figure. It clears the figure. You can see that ble.clf. It basically says clear the figure, and then it I'm not sure why CLF is before figure. I'll figure it out later. Okay, so it creates the figure, it clears it, and it creates an 8-inch by 8-inch figure. And it sets the X and Y limits. So the X limits go from -1 to 9, and the Y limits go, as you can see, from 24 to 18, which means the Y-axis is an inverted Y-axis. And that's because we are studying magnitude, right? The X label is the color. You can see that is the difference between magnitudes, and the Y label is the actual magnitude. Okay, so that is the color magnitude diagram. So let's define this function. You already know that functions can be defined without input. That's what we're doing here. And we are defining another function called write catalog. So what does this write catalog function do? Well, it creates smaller catalog from our larger catalog. As I said, if you navigate to the programs folder, you'll find the notebooks. But if you go one step up and you navigate to the data folder, you will see that there's GeckHST data text file, and this is essentially the full catalog, and we are going to create these files from scratch. So I can basically delete these files and I'd be able to create it using this notebook. Okay, so write catalog takes a catalog name. We are going to change it for every single type of star because we are splitting the main catalog. We are going to split it into the different groups that you saw in the HR diagram. So it opens the file using the open function, and then it opens it in write mode, and then it writes these individual lines where the parameter name string is provided as basically a line with all the data, all the data types. It prints all the data types in the top line, as you can see here, just like that. And then it loops over the parameters that you provided it, and it writes every single parameter in the right column. Okay, it spaces in between. One line stands for 1 star. Every single column, different rows at different stars, and every single column stands for one kind of parameter each. So let's define this write catalog function. Hopefully things will clear up when you see it in action, either today or tomorrow. So we are loading the data from the main catalog, the big catalog, GeckHST data.txt. We are using the load text function from NumPy. Data can be stored in so many different ways. This is a very simple data format. In astronomy, what we usually use is something called a PHAT file. If you're a SIP intern attending this session and you are going into an astronomy project this year, you will be sure to encounter some PHAT files at some point. But for now, we are working with a simple test file written in a simple format. And we unpack it to multiple variables. You can see how multiple assignments can work. Basically, it unpacks a tuple that comes out of the right side into multiple variables on the left side. So we have RA and DEC, which are kind of like the latitude and longitude in the sky. You have chi and eta, which is basically, in this case, all of these stars are taken from the Andromeda galaxy. So chi and eta essentially define the position of these stars with respect to the center of the Andromeda galaxy. I'm pretty sure that's what they are. So these are relative coordinates, chi and eta. And then we have these two different filtered names. These are the magnitudes in two different Hubble filters. And then we have the velocity measured from the redshift. We will learn what Doppler shift is tomorrow. And then we have the error in calculating the velocity. So I don't think we'll be using these two values. We'll only be using these two values, which are the magnitudes, all right? And then we define color using the difference of these two magnitudes, okay? I hope everything follows from Matt's presentation up until this point. Now, let's unpack the data and define the variable color. As you can tell, both of these variables are arrays, which is why we can subtract them. Subtracting two arrays subtracts the first element of the first array, the first element of the second array from the first element of the first one, the second element of the second array from the second element of the second element of the first one, and so on. It does an element-wise subtraction and creates a new array called color, okay? That's the magic of working with NumPy arrays. You can just do this kind of operations. They're very convenient. You cannot get this with lists. So we define the figure F and we initialize the plot. And then we plot a scatter of all the points. Scatter is kind of like plot, except we don't plot lines. We just plot the data points as they are, as points, okay, as dots, as little dots on the canvas. So the x coordinates will be color in the color magnitude diagram, and the y coordinate will obviously be one of the magnitudes. This gets F18, 14W. And then you can say what the color of the points will look like on the scatter plot. You can define the size of the points, and you can define whether or not the points will have an outline around them, and if the outline will have a color or how thick the outline will be. There's a lot of customization you can do in terms of looks. If you can imagine a plot, you can make it in Matplotlib, I promise you. There's nothing that this library cannot do. Okay, let's run it. Why does this not work? Because I did not add blt.show. Okay, plotted one, thankfully. You can see that the text looks a little bit different. It's not a sans serif font like the default one. It's a serif font. which is common in papers. And you can see that all the stars have been plotted in this color magnitude diagram. This is all the points we have, or pretty much all the points we have. There are some points outside this, but very few, which is why we have, clipped it to these X and Y limits. You can see that the magnitude goes from 24 to 18. It's a flipped Y-axis. You can see that there are different clusters. So let's take a quick look at these three different regions and wrap up for today. We'll address the rest of this notebook tomorrow. So you can see that there's a big cluster here, okay? This huge, very dense cluster here, right where my pointer is, right bang in the middle, okay? It seems to like spew out from here, the bottom, and it kind of stops here, right? Stops abruptly in a curve, all right? Beyond that curve, there are a bunch of points, okay? They're not as tightly clustered, but this is definitely a region. And on the left side, separated by this relatively empty channel here, okay, is this leftmost cluster of points, okay? So these are the three regions that we will separate and study tomorrow. I will stop here and pass the mic on to Jamika. Thank you, everyone.
Thank you so much, Aparajito. Yes, you stopped right on time. We have one question I think is perfect for you to answer right now. Do we need to save the notebooks before closing them right now?
Usually they save automatically, but you can just press Ctrl+S to save them just to be sure. Yes, you should save them.
Excellent. Any other quick questions in this last 30 seconds before we end today? Y'all have been amazing. Okay, I don't see any. I just got one here. Yes, thank you. Yes, so thank you, everyone. Madeline, Aparajito, Geronimo, and Raja has had to leave, but you all were absolutely amazing. Thank you so, so much. I'm going to, in my Zoom, give my little clappy emoji to say thank you. It really was fantastic. All the participants, you were amazing. Thank you for your flexibility and dealing with the issues with Slack. You put your questions and comments here and sent them to me, to us, and we shared them here, responded to it. It was absolutely amazing. I appreciate you so much. Yes. All right. And I know everyone has other things planned today. Thank you for sharing this part of your day with us. Madeline, Aparajito, Geronimo, thank you. Thank you so much. And Aparajito and Geronimo, we'll see you tomorrow for finishing up notebook 3 and then going into notebooks 4, 5, and 6. All right. I'll have this recording edited and posted on the Shadow the Scientist YouTube channel in the next few hours. And I've shared that link here in the chat. But let me put it here again for everyone. You can find it here along with the recordings of previous tutorials. And here is the Shadow the Scientist YouTube channel. And if you aren't subscribed to us, please do subscribe. All right, I'm going to go ahead and end this session. Have a great rest of your day. See you all tomorrow.
One quick thing
Yep,
before we go.
Aparajito.
I know a lot of people are having issues running the notebooks or installing them. And usually we try to help out in the Slack channel. This is exactly what the Slack is meant for, because you can share screenshots and we can work asynchronously, but unfortunately that's not working out. So I encourage everyone to check the original invitation email where you got this Zoom link to join this. There are a bunch of extra links there. One of the links should lead you to some pre-tutorial activities. Am I correct, Jamika?
Yes, absolutely. You are correct. Yeah. And I've definitely shared those with several people already.
Yes.
Again.
There's a bunch of Google Docs there that should walk you through the basics of running a notebook, Hopefully that will solve some of your problems. If you're having trouble installing it, I suggest Googling. Stack Overflow should help you with some of those issues, not just your Python, coding issues, but maybe you can find some of those answers with installation too. Yeah, we are just trying to work around the non-function, the problems with this. And yeah, over to you, Jamika. Thank you so much, Jamika, for taking care of the questions. That was really hard work, I know. Thank you.
No worries. My pleasure. My pleasure. And I did just, out of all those links that Aparajito was referring to, I put the link to the pre-tutorial guide for the Anaconda setup right here in the chat. But it is, again, all of this was a part of your Zoom confirmation email.